So good morning, everyone. Welcome back to Math 115. We absolutely didn't talk about anything before this recording started, just so you know. And so today we're going to talk about sections 3.1 and 3.2. Your homework, you had 2 homework assignments that were already due. Actually, today we're just going to talk about section 3.2. And you had 2 homeworks which were already due, but if you missed them and you need an extension until the end of fall break, just send me an email and I'll give you an extension. So the next assessment, okay, feels like it's far away, but it's not so far away. It's a week from today, on Wednesday, October 19th. That's the Wednesday following fall break. So the Tuesday before that day will be a review in class. So Tuesday, October 18th, we'll have a review in class, and I'll also have my office hours where I'll reserve a classroom and we'll have a big review session. So if you know anything about my office hours, you tend to get a lot of good practice, especially for the types of problems that show up on the exam. So I highly recommend coming to my office hours if you want to study well for the exam. I'll also post the recording to YouTube. So that's the exam. No calculators, as always. So if I put any logarithm questions on here, or if I put any exponential questions, it'll be something that you can do in your head. Okay, so that's the exam. It covers sections 1.4 to 1.9, 2.1 to 2.6, and 3.1 to 3.2. Okay, so the best way to practice, since the exam questions come from the homework, the best way to practice is to do homework problems without any external assistance, okay? And if you can do every homework problem that there is from these sections, which, by the way, it's not really that many. I feel like it's, well, okay, maybe I'm biased, but you could reasonably do every single homework problem between now and the exam. I think there would be no reason that you couldn't do that, especially if you work in groups. Yes? What about the compound interest?
Yeah, we're gonna get a calculator for that.
No, I'll make it reasonable. It'll be something like, I don't know, 100% interest, so that this number would be like 2, and then you take to a power or something like that. I'll give you numbers which it'll be easy to compute without a calculator. Okay, as long as you can do multiplication and division up to 12 times 12, you'll be able to do all of the mental math, or all of the by hand math on the exam. Does that answer your question?
Mm-hmm.
Okay, good. So regarding my office hours, they're going to be on Tuesday from 2:30 to 4 in LeConte 439. Actually, not in LeConte 439. They're going to be in a different room. But if you want to study for the exam outside of that, you can go to the tutoring center. I am told it is still open today, and it will be open on Monday, Tuesday of next week. So that's another great resource. So are there any administrative questions before we start in on content for today? Oh, one more thing. 3.2 homework will be due. I don't want to make the homework due the night before the exam, do I? Shoot. Okay, 3.2 homework will be due Thursday of next week. Thursday, October 20th, which means that I can't put 3.2 on the exam. So it'll just cover 3.1 from chapter 3. So less stuff to study. But then again, it's more stuff to study for the next exam, so. Okay, so that's what I'll do for 3.2 homework. So 3.2 will not be on the exam. So what we're talking about today will not be on the exam. So are there any administrative questions before we start? All right, it doesn't seem like there are, so let me remind you what we talked about last time. So last time we talked about the most important thing that you'll ever learn, maybe ever, which is about compound interest. Not just in math, but all of your disciplines. Okay, unless you count like basic human functioning, like eating and sleeping. I guess it's important to learn how to do that first. But this is the second most important thing that you'll ever learn in your life, which is how to understand compound interest and use this formula to determine the amount of money that you will have in the future. So basically we just take the principal, okay, and we multiply it by this number here, okay? So this number is given by 1 plus the interest rate divided by the number of times per year which we compound that nominal interest rate. And we take this to the power n times t, where t is the number of years that we invest for, okay? So for example, for 5% annual interest compounded semi-annually, we did $1,000, okay, multiply by 1 plus 0.05 over 2 to the 2 times 1. So this 0.5 here is the interest rate, this 2 here is the number of times compounded annually, semi-annually means twice per year. So this 2 is the same number, and then we multiply by the number of years which we invest for. So if we invest for 1 year, so for 1 year, then we put a 1 here. If we invest for 2 years, we put a 2 here. If we invest for 10 years, we put a 10 here. And then that, since this number is basically, this number will be larger than 1, so when we multiply it with itself successively, it will grow larger and larger and larger. Okay, and not only will it grow larger and larger and larger, it will grow faster and faster and faster, which is why your investment will grow the fastest in the last couple of years of its lifespan, okay? So, which is why when, you know, you're making the most amount of money on your retirement investment when you're like going from 63 to 64, 64 to 65, that's when you're earning the big bucks on your investments. So it's important to invest as early as you can, because that allows you to have extra time at the end of your investment to earn a lot more money. Okay, so that's compound interest. We also learned about continuous interest, where we, instead of using the number inside here, 1 plus r over n, we use the number e, which is something like 2.718 something something something. And the whole point of continuous interest is that we eliminate the number of times compounded yearly, because we're actually compounding and, you know, we're compounding continuously, right? Which means that we allow the number of times per year which we are compounding to grow to infinity, okay? To grow to infinity. That's what it means to compound continuously. So this was the formula for that. And then we did a practice problem where we compared 3 different banks using different interest models and ranked them in terms of which one would be the best or the worst, based on, well, it's the best if it gives us the most amount of money, right? Okay, and by the way, this is also reversed in terms of if you want to get like a mortgage or something like that, or you want to take out a business loan, then you want to have a low interest rate, right? Okay, so that was interest, and then we started talking about logarithms. So for logarithms, we basically, every time we have an operation in mathematics, we like to have a way of undoing it whenever possible, right? Sometimes it's not possible to undo things. But when it is, we like to be able to express how we do that. So for addition, the way we undo addition is with subtraction, right? And the way we undo multiplication is with division. And the way that we undo 2 to the x is with log 2 of x, okay? This is how we undo 2 to the x, okay? So logarithms undo exponentiation, okay? All right, so they are basically the inverse function of any exponential function. So if f of x is an exponential function, then the inverse function is what we call the logarithm with base a. And it has this property, right? So, okay, look, when we plug in 1 into 2 to the x, we get 2. When we plug in 2 into log 2 of x, we get 1. It reverses the process, okay? So the output of the log function is whatever the input should be for the exponential function in order to get the input of the log function, which I recognize is basically a run-on sentence. It's kind of confusing, but let's see some practice. So we basically had this relationship here which said, well, anytime I have an equation which is written in exponential form, I can rewrite it in logarithmic form by using this phrase, log base argument equals exponent. So that tells us where each number in the exponential equation should go in the logarithmic equation, okay? So the base should go where the base is, the exponent should go to the exponent spot, and the argument is the answer or whatever is on the other side of the equals side. Equals sign. Okay, so we practiced converting, and then we started learning some properties of logarithm functions. Actually, we learned how to evaluate logarithms first. There are some circumstances where we can evaluate logarithms by converting into exponential form. When we convert into exponential form, if, and this is quite a luxury, if it's easy to see what the power should be, like in this case, 5 to the what is 25, it's easy to see that the power should be 2. If we have that luxury, we can solve for the answer of this logarithm just using by transferring it into exponential form and seeing what should the power be. Okay, if not, then we're going to be relegated to using our calculators, which we're going to talk later about how we do that. Because you're going to notice that there's no log 5 button. There's no log 1/3 button. Okay, but we're going to see later how that's not a problem. Okay, so then we talked about properties of the logarithm. So, okay, these are pretty simple. Since a to the 1 equals a, if we convert this into logarithm form, okay, we get this equation. Log a of a is 1. Same deal if I do log a of a to the x, right? So a to the x equals what? A to the x, right? So we put a to the x, which is the argument, we put it in here. We put the base right here, and we put the exponent right here, right? So that's how we get that equation. So what does that mean? That means that log a and a to the x undo one another, right? They are inverses. And same thing in reverse. If I plug the function log a of x in for x in the function a to the x, it undoes that process, and we just get back x. Okay, so these functions are inverses of one another. Since they are inverses, it's really easy to tell what the domain and range should be. The domain and range of a logarithm is just the opposite of the domain and range of a exponential function. So an exponential function has domain all real numbers and range 0 to infinity. So likewise, the domain of a logarithm is going to be 0 to infinity, and the range of the logarithm is going to be all real numbers. Okay? So are there any questions on what we talked about last time, starting off with these logarithms? Or anything you'd like me to explain in a little more detail? Okay, if not, then let's move on to today's content, which is how to graph logarithm functions. Okay, so logarithms are functions just like exponential functions are. Okay, and the way we're going to graph them is going to be similar, right? Is going to be similar. We're going to ask ourselves, well, what are the 2 points that a logarithm always passes through? Well, we know that f of x, what should I say here? I should be careful about my mathematical language. We will call f of x equals to logarithm of x, and we know that f inverse of x is a to the x. And we know that on the graph of a to the x, we always have the points what? What are the 2 points which are always on the graph of a to the x? 0, 1. Why? Because when I plug 0 in for x, I get something to the 0 power. And anything to the 0 power is always 1. So 0, 1 is always on the graph. And what is the other point which is always on the graph of an exponential function? 1 comma a. Why? Because when I plug in 1, anything to the first power is itself. So a to the 1 is a. So I know these 2 points are going to be on the graph of the inverse function. So what are the 2 points which are going to be on the graph of f of x equals log a of x? We're going to have 2 points, which are going to be the points what? They're not going to be these points, are they? But they're going to be informed by these points, right? What are we going to do?
Do you just like invert them?
Yeah, we just invert them, right? It's the inverse function. If the whole point of the inverse function is that if you plug in the output of your original function. You should get back the input, which is the requisite input needed to get that output for your original function, right? So when we plug in 1 into the function, since f of 0 is 1, we know that f inverse of 1 is 0, right? And this is how we get points on a function, right? The height of the function is just what I get when I plug in a number into the function, right? So 1, 0. And the other one will be a1. Okay, so let's take a look at two graphs. The first graph I'm going to make is going to be the function, why don't I use pink for it, f inverse of x is going to be a to the x. So let's graph it. It goes through the point 0, 1, and it goes through the point 1, a, right? So this is 1a, and this is 0, 1. So what does the exponential function look like? It looks something like this. Yes? Something like that. Okay, that is what the inverse function looks like. We know, actually, also that the graph of any inverse function is going to be similar to the graph of this. Does anyone know how it's going to change, though? What relationship does the graph of the inverse have to the graph of the original function? Sorry? There is a symmetry. What kind of symmetry? About the line y equals x. Is that what you said? Yeah. So we're going to have a symmetry. It's not going to be a symmetry like this, okay? And it's not going to be a symmetry like this. It's going to be a symmetry where we flip across this line. Okay, so let me draw in the line y equals x. So this is the line y equals x. And now let's draw what is the graph of f of x going to look like, which f of x is log a of x. So what am I going to do? I'm going to take a point here, and it's going to get mapped straight across this line. I'm going to take a point here. It's going to get mapped straight across this line, and so on and so forth. Okay? So what is it going to look like? Instead of approaching the x-axis here, our function is going to approach the y-axis down here, right? So our function is going to look something like this. Okay? And it passes through the point 1, 0 and the point a, 1. Okay? a, 1. So this point, we just reverse the coordinates, right? We reverse the coordinates of the other points. Yeah? I forgot to put in parentheses here. Okay, so this is how we get the graph of the logarithm. So all the logarithm functions are going to look something like this, right? And you can see that we have a vertical asymptote, right? Why do we have a vertical asymptote? Well, we have a vertical asymptote because the inverse function has a horizontal asymptote. And this vertical asymptote reflects the domain of the logarithm, right? What is the domain of the logarithm? The domain is from 0 to infinity, right? Makes sense because we've got a vertical asymptote here. We've got a vertical asymptote here. So we're not going to plug in 0 into the logarithm, are we? No, we're not. Okay. That's because, why is 0 not in the domain of the logarithm, by the way? 0 is not in the domain of the logarithm because 0 is not in the range of the exponential function. You're starting to see this kind of relationship here between these inverse functions. They're very closely tied together. Okay, are there any questions about how we make the graph of a logarithmic function? Mm-hmm.
How did you know where the A was?
How did I know?
Like on the graph.
You mean like the picture? Like how did I know that A was here and not out here?
Yeah.
Is that what you mean? I didn't. It's just a demonstration. So you know, for example, a can be any number that you want, right? It could be 2, right? And then this would be about right, you know? But I'm not actually trying to make this graph to scale. What I'm trying to show you is, in general, what will the 2 points be on the graph? So if you're doing log 3 of x, then what is this point going to be? It's going to be the point 3, 1. If you're doing log 4 of x, it'll be 4, 1. If you're doing log 1,000,000 of x, it'll be 1,000,000, 1. So I don't actually know that this point exists here and not, say, over here. It's just that I'm trying to kind of demonstrate that it's going to be up and to the right of 1, 0. Does that make sense? Good question. Are there any other questions? All right, doesn't seem like there are, so let's try one together. Maybe we can do this as a partner practice. Okay, so let's get into our groups here. We have the graph of log a of x, and now what are they trying to get us to do? They, I say they, it's me, right? Okay, but they are trying to get us to graph negative log 3 of negative x. So again, we can use the theory of transformations to try to make this picture, okay? So go ahead and work with a partner and try to draw as best you can the graph of negative log 3 of negative x. And I'd like you to make sure to label the 2 points that this function is guaranteed to pass through. All right, so go ahead and get started with the partner. Andrew, you want to go work with Haley? Thanks. And Jenna, can you go work with Liam?
What a regular log looks like.
And then Maya, can you work with Lawson?
So this is a reflection of the x-axis and a reflection of the y-axis. Yeah.
Is that allowed? It's a question, right? Yeah. Well, I think we agree that we can't do the log of a negative, right? But if x is negative, then negative x will be positive, right?
No.
No? Okay.
I don't know where I'm just
Well, it's just practice. So when you do a lot of math.
So is this the original? This would be like the original.
Same thing as like when you like multiply a negative number by a negative number and a positive.
Mhm.
Okay.
And then the reflection.
Yeah, exactly. Yeah. Sorry?
So that
There is your it's x.
But it's equal to negative.
Okay, so let's ask ourselves really quickly. All right, I think there's some confusion here. There's some confusion here about, wait a second, Tom just told me that I'm not allowed to plug in negative numbers into this function, and now he's trying to pull a fast one on me and make me do the log of a negative number. So is it a trick? No, it's not a trick, because think about the following. If x is negative 1, then what is negative x? It'd be 1, right? And I can do log of 1, that's fine. Do you see what I mean? So what is this going to reflect? Well, I mean, literally, reflect, right? This is going to be a reflection about which axis? About the y-axis, if we have a reflection here, right? So it's not going to be going like this, it's going to go like this. See what I mean? And then what's this gonna do? Yet another reflection, right? But not about the y-axis. It's gonna be about the other axis. Does that make sense? Okay, maybe we can just do this one together.
Yeah.
Okay, it's confusing, right? But
Quite literally.
okay, but here's the deal. All I'm gonna do is I'm gonna make this picture, except I'm gonna apply two transformations. The first transformation that I have to apply is a horizontal reflection. And the second one is a vertical reflection. If you want, you can say that these are about the y-axis and about the x-axis. So what does it look like if I take this function and I reflect it about the y-axis? It looks like this, okay? So that's this one done. And then what do I still have left to do? A vertical reflection about the x-axis. So instead of looking like this, it's gonna look like that. So now I need to ask myself, what are the 2 points that are gonna be on here? Well, I need to take the point a comma 1. The first thing I need to do is move it over here to negative a comma 1, right? The way I do a reflection about the y-axis is I change the x value of every point from being positive to being negative, or from being negative to being positive. So I change the x value a to being negative. Now I still need to do the vertical reflection. So the vertical reflection means I'm gonna do what? Move it across the x-axis, which means what is the new point gonna be? It's not gonna be here, it's gonna be down in quadrant 3. Yes? And what would the coordinates of that point be? So negative a, because the x-coordinate hasn't changed, has it? But what happened to the y-coordinate? It should be negative 1 instead of 1. So let's take a look at this. What are my 2 points going to be? Well, on the original function, I had the points what? On the original function here, the parent function is log 3 of x, right? So what are the 2 points that are going to be on log 3 of x? It's going to be the point 1, 0, and the point what? What's the other one? It's not 1, 3, because 1, 3 would be up here, right? This is where the 1 x value 1 is. So 1, 3 would be up here. So this one's going to be not 1, 3, but 3, 1. Okay, so now what do? We take the point 3, 1. We move it over here and then down here. So its coordinates are going to be down here. What are the coordinates of this point? Negative 3, negative 1. And how about this point here? Negative 1, 0. Very good. So this is the graph of this function. Okay? Does that make a little more sense now? Okay, so what we're doing here is nothing special. It's just what we have always done with these transformations, but maybe I think part of the confusion could be coming from the fact that reflections are one of the hardest ones to do. Is that maybe why this is a little harder? Okay, so reflections are tricky, but what we need to remember is if we do a reflection, all we're gonna do is we're gonna take all of the points on the graph and we're gonna change the sign of one of the coordinates, depending on whether it's a y-axis or an x-axis reflection. Since we're doing both, we're gonna take the points which are on the graph of our original function, and we're going to change the sign of both coordinates. So instead of 3, 1, we have negative 3, negative 1. Instead of 1, 0, we have negative 1, 0. Why didn't 0 change? Because negative 0 is the same as positive 0, right? It doesn't have a sign. Does that make sense? Okay, so 2 reflections just means we change the signs of each coordinate. Okay. Any questions on this one? Okay, I have a question for you all. What is the domain of negative log 3 of negative x? What's the domain? Well, can someone tell me first, what is the domain of a function? All of the x values, specifically, not all of the x values, all of the x values that are allowed to be plugged into the function. This is what the domain is. So I get a big bucket and I collect all of the numbers which I say, this one's okay to be plugged in, this one's okay to be plugged in. Oh, you are not okay, I'm not gonna put you in the domain, right? So this big bucket full of numbers which are allowed to be plugged in, right? What are the numbers which are allowed to be plugged into this function? Yeah, only negative numbers. The domain is going to be negative infinity up to 0, not including 0. Why? Because these are the numbers that if I plug them in here, right? Let's take -5 for example. If I plug it in here, I'm gonna get -5, which is 5, right? So negative numbers are the only numbers which are allowed to be plugged in because if I'm doing a logarithm, the logarithm needs to be done on a positive number. But since I'm doing negative x here, I need x to be a negative number so that negative x is a positive. Does that track? Okay, how about the range? Yeah, all real numbers, right? All real numbers. Logarithms, their range is always all real numbers. You can kind of see why, right? Any height that you want, you can achieve with a logarithm. Okay, so that's this problem. How much time I got? Okay. So let's talk. Okay, any questions about domain and range of this function or about how to graph it? Okay, if not, then we move on to a new topic, which is the natural log. Okay, also known as the best one. Does anyone know why natural log is the best log? And I don't mean my favorite, I mean it's the best. The natural log is the best log because it's the one that's on your calculator. Okay, that's why the natural log is the best log. Okay, so what we're gonna do is, in a minute here, we're going to discuss, okay, how do I do something like log 5 of 26, right? How do I do something like log 5 of 26? What we established last time is that if log 5 of 26 is the number I'm after, then the corresponding exponential equation would be 5 to the x equals 26, right? And remember we said, well, okay, what the heck is that? What is x? What power of 5 do I have to take to get 26? It's gonna be like 2 point something, right? So the way that we're actually going to evaluate this is, well, it'd be nice if we could just type in our calculator, log 5 of 26, and it would tell us what that number is. But most calculators don't have that button. They just have an ln button. So we're going to see how to reformulate this problem in terms of natural logs so that you can plug it in on your calculator and get the answer. Okay, so that's where we're going. But first, let's talk about the natural log, which the only thing that you need to know about the natural log is it's the logarithm with base e. So remember, e was that number like 2.718 ... right? So lots of other decimal places after that. So this was the number e. So if I take the log e of x, okay, if log e of x is equal to y, then what's the corresponding exponential equation for this logarithmic equation? Yeah, this is e to the y equals x, okay? Log base argument equals exponent. So the base is e, the argument is x, and the exponent is y. So this is the corresponding exponential equation, okay? So e is a number like 2.718 da 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 da. Okay, so you can think of what is log base e of 6. Well, that would be the number y such that e to the y is 6, which is the number such that 2.718 dot dot dot. And I take that to the power y, and I get 6. So this is the number that I want to find, the number y, such that if I take 2.718 to that power, I get 6. So this is logarithm with e, okay? Nothing different. The only thing that's a little annoying is it's not a whole number. So you think, well, letters are scary. But this is just a letter which represents a number, okay? So e never means different numbers. Anytime you write e, you're always talking about the number 2.718 dot dot dot. Okay, so what are the properties of the natural log? By the way, the shorthand is ln. I feel like it should be nl, but whatever. ln of x is what we write instead of log base e. So ln of e, log base e of e is always 1. Log base e of 1, still 0. Why? Because 1 comma 0 is always on the graph of a logarithm, right? ln of e to the x. These two functions are inverses, right? E to the x and ln x are inverses. So if I plug one into the other, right? If I plug e to the x in for x in ln, I should just get x. And if I plug ln of x in for x in e to the x, I should get x. This is because these functions are inverses. So these are just the same rules that we already talked about, but rewritten in terms of this new notation for ln. Okay, so why is ln important? ln is important because it is on your calculator, and we have the following extremely important formula. Following extremely important formula, which is called the change of base formula. So if you want to do log a of x, the shortcut by which you can use your calculator to calculate this log instead of looking through a really big book of logarithms, okay, is you can rewrite the log a of x as ln of x divided by, oh, this should not be ln of b, this should be ln of a. I don't know how a b got in there. ln of a. Okay, so we just take the natural log of x divided by the natural log of a. So let's see this in practice. If I want to do log 5 of 26, I want to do log 5 of 26. Well, this is equal to what? ln of 26 divided by ln of 5. Okay, so let's see here. Maybe I can go to like Wolfram Alpha. Let's see here. Internet. Wolfram Alpha. Let's see how this works. So what we're trying to do here, hello. What we're trying to do here is compute log 5 of 26. So what would I do on my calculator? I would plug in something like ln of 26, and I would divide that by ln of 5. Okay, and we get 2.02 something, right? So, like we said, the power that we need to take 5 to in order to achieve 26 is this number. So if I take 5 to the power 2.0243, all of that, then I get 26 as the answer. Okay, so why is this important? This is important because the ln button is on your calculator. You can type ln on your calculator. There's no log 5 button probably, on your calculator, unless you have a really fancy one. Okay, so this is why the change of base formula is so great. This is how I would type it in on my calculator, okay? So just to show you that this is true, we can say, we can get Wolfram alpha to evaluate the truth value of log 5 of 26. Let's see if it likes that. All right, I go true. Hell yes. Okay. That's what we wanted to be true, right? Okay. So by the way, if you use Wolfram alpha, or if you, in a lot of different books, when people write just log, okay, there's some people who, okay, you might have been taught in middle school that if you write log with no base, it means log base 10. Most of the time in math literature these days, log with no base means natural log. That's just a notation thing. Okay, so are there any questions about the change of base formula and why it's so great? Or why natural log is the best log of them all? No? Okay. So, okay, you probably, who has a calculator on them right now? Okay, that's a problem. All right, well, how would I go ahead and calculate these? Okay, yeah, I shouldn't have put this as an example for partner practice. We're not going to do this as partner practice, but you do need to know how to do this. So what would I get if I did log 2 of 7? It's just going to be what? Change of base formula. I'm going to rewrite it using natural logs. What would it be? It'd be ln of 7 over ln of 2, right? How about the next one? Uh-oh. Is it an uh-oh? This would, no, this, we can do this, natural log, right? It's just change of base formula, ln of 1 divided by ln of 10, right? Is this okay? No, why is that not okay? Something is really bad here, right?
Yes.
What is it?
You can't have a negative number.
I can't have a negative number. Why not?
Because you said so.
Because I said so? No, we should always believe things because we have good reasons to believe them. Why can I not do ln of 1? Because if ln of negative 1 is equal to x, then what's the corresponding exponential equation? Well, what's the base? E. So E, what's the exponent? X. And what's the argument? Negative 1. What's wrong with this? It's not possible, right? I take a positive number to any power, it's always going to be positive. So there's no way to get negative 1. Okay, so this is a big no-no. We can't do something like log 10 of negative 1. Not possible. All right, well, we'll probably stop there and pick this up next time with some log rules. So have a fun and safe fall break, everyone.
Try not to freeze.
Yeah, I'll try not to die of freezing.
I'm definitely going to need an extension for the homework, so do you still want me to email you? Or?
Yeah, please do.
Okay, I will. Thank you. Have a good homework.
Yep.